Well, hi there, sports fans. Welcome to another edition of Physics 12. This is lesson 2.5. We're going to be talking about the Atwood machine. So, what is the Atwood machine? Well, the Atwood machine is an invention to allow things to be lifted more easily. So it gives you some assistance when you're having to lift heavy objects. And an example of this is the elevator. And so if we look at the sort of basic structure of an elevator, this is really all it is. All it is just the elevator car, and you have a cable attached to it, goes around the pulley. Now the pulley itself is connected to a motor, which will actually do the movement of the elevator, but you have a counterweight on the other side there, and that's what allows the elevator car to be lifted much more easily. And also much more controllably as well. So there's less stress on the motor mechanism in order to move the elevator up and down. So if we look at the orientation of this, we have the mass here is the M1 is the mass to be lifted, and in the elevator case that would be the elevator car, and then M2 would be that acts as the counterweight in this sort of arrangement. So if we look at an example, we'll put some numbers in here. So find the acceleration of this particular system and the tension in the cable, and we'll add some numbers to that. So let's say the elevator car has a mass of 1,150 kilograms, and its counterweight has a mass of 1,000 kilograms. And so you can see right away that if you need to lift this mass right here, it would be a whole lot easier to do when you have a 1,000 kilogram counterweight over on the other side. But we're not really looking at that specifically right now. What we want to do is we just want to look at the acceleration of the system based upon the masses that we have here. And there's a way of doing this which makes good use of algebra once again. So the place to start, once again, is with the free body diagram, and you will be hearing that refrain throughout the year, so you're hearing it here again. Now, like what we did last time, there's a trick in terms of drawing the free body diagram, which is going to make it a whole lot easier for you. And the way we do that is that we're going to draw all the forces in the x direction. And you can do that because, well, you can do basically anything you want as long as it makes sense. So, as long as all of our forces are drawn correctly on the masses, we can put them all in the x direction. Now, in a lot of cases, that's not going to help you when the problems get to be more complex and in 2 dimensions, etc. But for our purposes, for this kind of a problem, that works very well. So let's see how that's going to work. So M1, it has a mass. And the down direction will just make to the left, and the up direction will make to the right for this one. So we have a force of gravity to the left, and we have the tension in the cable to the right. And then the counterweight, it has a tension force to the left, which is now the positive direction. And it has a force of gravity down, which is to the right in this particular case here. So you can see this makes it a whole lot easier to deal with. When you have a pulley, we'll just make all the forces in the same, well, in the x direction. All right. So again, good place to start. F equals ma. You really can't go wrong here. And so we'll write the force equations for each one of the masses. And when we do that, then for this one here, we have tension, which is in the positive direction, minus the force of gravity. That has to equal the mass times acceleration of this particular mass here. This one over here, the force of gravity is in the positive direction, and the tension force is in the negative direction. So for M2, the force of gravity minus the tension equals the mass of 2 times the acceleration. All right, so we'll put the numbers in here. So we have T minus 1,150, which is the mass of this, times the force of, or the gravitational force, which is 9.8 meters per second squared, equals 1,158. So that's our equation from this mass, and then the equation from the other mass is just simply 1,000 times 9.8 minus t equals 1000a. So let's put those two equations together. And as you can see, when you put them together and you add the equations together, then the tensions will cancel each other out. And then we're left with this right here, which we can easily determine. I trust you can do the math here. We will get an acceleration of minus 0.68 meters per second squared. All right, and then once we have that, then it's an easy matter to find the tension. We can use either one of these equations to find the tension. We just put the number in that we have for acceleration. And be careful, you've got to trust in your plus and minuses. If you set up the equations correctly, our acceleration is negative here, so we need to make that negative over here. So watch out for your plus and minuses there. But if you have your plus and minuses all correct on the way through, then again you can trust your answers there as well to have the correct plus and minus. And so when we put the number in there for acceleration, then we get the tension in the cable at 10,490 newtons. All right, so that deals with that one there. And so just wanted to go over another type of a problem here. This is similar to the many body problem, except in this case now, instead of having some kind of a string or rope between the masses, now all it is just three masses that are in contact with each other, and you have an applied force that's accelerating the system. So for this particular example, what we're going to do is we want to find the acceleration of the system, and we want to determine what the contact forces are between each of the blocks. So in other words, what are the forces that are in between these blocks here? And the numbers we have here, we'll make each of the masses just 4 kilograms. We'll just make them all equal just to make it a little simpler here. And so we are should have the force on here as well. That was going to be 96 newtons. The applied force is 96 newtons. Oh yeah, we've got it right down there. Okay, so yeah, we have all our numbers here. So we'll write down, so we're going to start with our free body diagrams, and we'll do one for each one. So the first mass, it has the applied force on it, but it also has the force of the second mass onto the first mass, and it's in this direction. For the second mass, it has the force of the first mass on it in that direction, but it also has a force in that direction from the third mass on it. And as you can see, this is very similar to when you have the strings in between them, you will have equal and opposite forces between the masses, and this is the same kind of thing. So lastly, we have the third mass. The only force on the third mass is produced from the mass of the second one onto the third one. All right, so now we can write down our force equations for each one. F equals ma, we'll start with that, you can't go wrong with that. So the forces, some of the forces on this one is the applied force minus the force of the second mass on the first mass. That has to equal 4a, because each of these masses is 4 kilograms. The second one here, you have the force of 1 on 2 accelerating it. And just want to make sure I've got the numbers correct here. Sorry, I should have these numbers switched around. This should be 1 on 2, and that should be 3 on 2, like so. Sorry, I had those backwards. Okay, so we have force of 1 on 2 is positive, so the force of 1 on 2, and then we have the force of 3 on 2, which is negative, and that has to equal 4a as well, because this is 4 kilograms. And lastly, the force of 2 on 3 has to equal 4 times the acceleration of mass 3. Okay, I think I got them all correct here now. So let's put all these equations together. And so there's a free body diagram. Here's our equations. And once again, we're going to add all of the equations together. And when we do that, you can see these two will cancel out because the magnitudes are the same, but the directions are opposite. And similarly with these two, these will cancel out as well because the magnitudes are the same, but the direction is opposite. One's positive, one's minus. So now when we add these together, then we get 96 equals 12a. Add those three together. And now we can find the acceleration of the system. So 12A equals 96, and then A is 8 meters per second squared. So each of the masses is accelerating at 8 meters per second squared. Now we want to just find the tension, or sorry, the force, the contact force between each of the masses. And that's easy to do. We just go back to the a couple of the other equations that we had. And so this was one of them here. You work it through, and you get the force of 2 on 1 is 96 minus 32, which is 64 newtons. And then lastly, to find the force of the second mass on the third mass, then that works out to 32 newtons. So essentially, it looks like this here. So we have an applied force of 96 newtons, accelerating the system at 4 meters per second squared. Yeah, 4 meters. No, sorry, it would be 8 meters per second squared. Sorry. So the system is accelerating at 8 meters per second squared. And so the contact force in here is 64 newtons, and the contact force here is 32 newtons. And we just want to see, does that sort of make sense? Okay. Well, we have our applied force, which has to accelerate all three. Now, this one here, the contact force from here has to accelerate these two masses here, which their total mass is 8 kilograms. So we need a 64 Newton force pushing on those two there. So part of the applied force here is accelerating this mass. What's left over is accelerating these two. And then if we look at the contact force right here, then once again, we need a 32 Newton force accelerating this one at 8 meters per second squared. And again, that makes sense because this applied force, first of all, when it accelerates these two masses, what's left over is accelerating this one here, and that is 32 newtons. So it all kind of makes sense if you think it through logically and intuitively.